Hello, everybody. I'm Asen from V-Ray R&D team, and today I'm going to present to you little research that we did last year, and it is related to V-Ray adaptive dome light. So, in 3 months, we will have the opportunity to present this research at SIGGRAPH 2018. And this will be just a talk, because it's a small research. But I want to use the opportunity to show you the paper. This is just a two-page short paper. And I want also to use the opportunity to show you all the collaborators, because there were a lot of people involved in this work. And this work initially started with the V-Ray adaptive lights in V-Ray GPU team. And then we decided that we can take advantage of this work, and we started to work on the CPU version of V-Ray adaptive dome light. And then the GPU team helped us to implement this also in GPU. So today I will present you some results on V-Ray CPU and GPU version. I will need less than 50 minutes to tell you all of this. So I decided to start with a brief introduction into the topic, because I know that there are many students here, and I really wanted to give you an introduction and to really make this more like a lecture, and in the end it will be like a research talk. And I hope this will be accessible to more people. So, a quick overview of what we're going to hear today. I will speak about this dome light, what it is, a few words about image-based lighting. Actually, these words in the brackets here have a lot of in common and are nearly the same thing. The image-based lighting, which in V-Ray is implemented as a dome light. It is also an infinite area light, which surrounds the whole scene with infinitely large sphere. And we use this image. This is an HDR image. We use this image that surrounds the scene to lit our scene geometry. So I will say just a few words about radiometry in order to be able to define the BSDF, which is the mathematical tool which describes materials. And then we will need the BSDF in order to define the scattering equation. This is an equation that describes how light is reflected, is scattered at a point, and we need to be able to define and solve this equation in order to compute images. Then I'll speak a little bit about Monte Carlo, how we usually use Monte Carlo methods to solve this scattering equation. And I will speak about then multipoint sampling, which is a very practical and very crucial tool used nowadays in computer graphics. Then I will tell you what is the classical way to compute this image-based lighting. This is something that is that you can find in almost any book for photorealistic rendering. So if you want to read more on this, you can, for instance, read physically based rendering. And then I will explain our two-phase adaptive approach, which is very simple, and it is built on the top of this classical approach in order to get better results. So let's start. This is one panoramic HDR image, which describes spherical environment, and we can use such images like this one here to lit our scene. So this is a very simple example of scene lit by this same HDR here. We use this spherical mapping in order to describe the lighting for these scenes. So we have 3 balls here with different materials. The left one is a mirror material. The middle one is a glossy reflective material. And the right one is a pure white glossy material. So one thing that I'm going to explain today is how different materials need different sampling strategies in order to be computed efficiently. Now, radiometry, I want to just give you a few slides on this. This is a branch of optics, and radiometry basically describes the distribution of radiation in space, the distribution of power in space. So we are obviously interested in the visible spectrum, which is above on the picture. And in one of the most basic quantities in radiometry will be shown in the next slides. So first of all, we have the light energy. This is intrinsic property of light. Each photon has this. Each photon, depending on its frequency, has a different amount of energy. So if we want to measure this energy, we need to define this the notion of power. The power is the energy per unit of time. Then we have the quantity of irradiance, which is basically the power per unit area. So we can measure power at a point. It is measured in watts per square meter. And next, if we want to go even further, we can derive the power, the power at a point which came from certain direction. Here, this is the direction O. So if we integrate all the radiance over this hemisphere here, this is a hemisphere on a surface, and you can see here the vector normal n, and there is an infinitesimally small piece, small patch around the point x, and small solid angle around our direction O. So we can integrate it. You can see the equation below. If we integrate, for instance, all the radiance that is coming from everywhere, we can get the irradiance. So this is an important concept because it is used for pointwise computations. Basically, in a ray tracer, when we want to simulate white, we want to measure this radiance along different rays. Now, the bidirectional scattering distribution function is a function defined over the surface, which describes the properties, the material properties. And from now on, I will use this notation that the direction I is the light from which light is incident. This is the incoming light direction. And the blue, the O direction, is the direction to which the light is reflected. So the BRDF is this ratio is the ratio of the light that came along direction I, and it was reflected exactly along direction O. So these materials need to have meet certain properties in order to be physically based. So one thing is the second point here, the second bullet. This is the reciprocity. It means that the material should behave exactly the same way, no matter if the light is coming along I and we are measuring or observing at O, or vice versa. And also energy conservation must be met. This is the last equation here. So what we are trying to solve is this. This is the scattering equation here. We have a virtual camera, we have a ray, and we would like to know exactly how much radiance is reflected from the scene along our ray. And in order to find this, we need to integrate all the incoming light. The incoming light here is with orange. So this is incoming light. The light curve is the BRDF function, which for a fixed direction O is just a spherical surface, which says how much light will be reflected from the corresponding direction towards our camera. And anything else here? So today I'm going to speak of how we solve this equation. Now, in the special case of dome light, the dome light here is the orange. All the light is coming from all different directions, and I have exchanged here the light incident at the point with the light which is coming from the dome light. This is LD, and this is the visibility functions, which only says how much light is actually reaching the point, because there might be some occluders that stop the light, like this transparent object here that I have drawn. But basically the equation is just the same. So now just a few words about Monte Carlo methods. Monte Carlo methods are numerical methods that basically these are integration methods. They compute approximate solution, and they have some very unique properties. For instance, when you compute something with Monte Carlo, you have control of accuracy. You can say, I want my solution to be precisely that accurate, and you can wait until this accuracy is reached. Or the other thing, which is that you can have control of execution time. You can say that, for instance, you want your algorithm to work for 1 minute or 1 hour and just to see some result, and Monte Carlo methods give you this. Monte Carlo methods converge very slowly, but they converge with this convergence speed here, 1/n², regardless of their dimension, which does not apply to other methods for numerical integration. And yeah, so I want to show you here, this is the basic Monte Carlo estimator. We have an integral of the function f of x in the interval a to b, and we would like to compute this integral. So we just compute the function in some points inside the domain. These points, oh, you saw my presentation. I'm so sorry. Okay, so these points are uniformly distributed here, and if we just sum up and average all of these points, we have an estimate of the integral. So a little more advanced is if we have a particular density according to which these points here are distributed. So we just have to weight all of these samples with their probability of being chosen. So you can see that this formula here is a generalization of the formula above, because if P here is a uniform distribution with probability 1/b minus a, we will get exactly the formula above. And the other very important thing about in Monte Carlo estimating is the importance sampling. This is something that we are going to use a lot today. So in order to use importance sampling, we try to find such probability density. You can see the line below. We're looking for such a probability density P, which is as close as proportional to F as possible, because in the best case, when P is directly proportional with some proportionality constant of C to F, what happens is that P is a probability density. It must be normalized. So when we normalize it, we find that C is 1 over the integral that we are trying to compute. So basically, in this case, we need just one sample in order to find the precise value of the integral. Of course, this is not the case most of the time, but this is a very important observation and used widely in computer graphics. So I'll try to, now we'll go into practice. So we have here the integral that, the scattering equation that we wanted to solve. And this is the most simple way to discretize it and this is the most simple form of the Monte Carlo estimator. It's just a sum over and we compute the function which is under the integral. We compute it in different directions, and these directions in this case are distributed with this probability density P, which is in the denominator. So if we can do this, we can start to compute these estimates. Next, I want to tell you what is the importance of using different strategies when sampling such integrals. Now, in all of these cases, in all of the 4 cases, we have a surface, we have a point, we have 2 different materials. On the first row, we have a diffuse material, and on the second row, we have glossy material, which can reflect light only to a certain direction. The orange arc is our dome light, and I have drawn a sun because it is very common case when we have these HDR images and we have some very bright spots, and the other is just much lower. So when the left column is the sampling strategy of the light. So this is the sampling strategy of the dome light. The dome light tries to generate directions to those parts of the HDR image which have high intensity. So the best thing we can do in this regard is just to generate arrays proportional to the environment map. And in the case, for instance, you can see here that we have a lot of we have a lot of rays that point to the sun because it has the highest intensity. And in the case of diffuse material, this is the first row to the left. This is our perfect scenario because here the white arc, this is the BSDF. This is a perfectly diffuse BSDF, and it can scatter light. It can scatter light in any direction, no matter where the light is coming from. But this is not the case on the bottom left picture, where the material is glossy, and we generate some rays that point. Most of them point to the sun, but the material can reflect only light from certain directions. On the other side, there is the right column. This is the strategy of the material. So the diffuse material can generate rays according to its value. So the BRDF tries to generate more rays where the BRDF is high. So in the upper case, it just generates uniform random rays on the hemisphere, which in some cases it may be efficient, in some cases it is not efficient, because you can see we waste a lot of computational effort, and maybe just a small amount of these rays will hit the actual the bright spots on the environment. And on the other hand here, if we have glossy material or nearly specular material, it is much more efficient to generate rays proportional to the material. Because if we generate, for instance, a direction from the light, it is very unlikely to find this small direction from which the light will be reflected. So that's why we have these these two general strategies, the light sampling and the BSDF sampling, and we need a way to combine these sampling strategies in a good way. We cannot just blend between them because they will introduce a lot of variance. So here is a classical example. This is from the PhD thesis of Eric Visch. So this is a very interesting example. We have 4 lights shining on 4 different types of surfaces. All the 4 lights have different sizes, but they emit exactly the same amount of radiation. The surfaces, on the other hand, the surface which is closest to the light sources is almost specular, almost a mirror, and then it starts to get rougher and rougher, and the surface here, this one here, is very rough. And we can see a comparison between the two strategies. The strategy that samples the material works well in some cases, while in other cases, for instance, for very rough materials and very small light sources, it generates a lot of rays, but very few of them are actually able to intersect the light. On the other hand, we have here the strategy where we pick a point on the light source and we try to connect this point with a shadow ray to our shading point. So it works well in many cases, but there are other cases, for instance, for very shiny materials and for very large light sources, where we pick a point on the light, but we can hardly find this direction along which the very specular lobe of this material transfers light. So this is just a very good example of how the two strategies have different strengths and different weaknesses. Now, Eric Visch came with this simple and very powerful, very practical idea called multiple importance sampling. And this is a way to combine different strategies in a provably good way. What it is, I will explain just with a few words what is the multiple importance sampling. This is something used a lot in graphics. So we have an integral to estimate. This is on the left side. And this is something very similar to the simple Monte Carlo estimator, but instead of one sampling strategy, we have this PI. We have multiple sampling strategies and sampling strategies, and we have NI samples taken from each of these sampling strategies. And we have sampling weights on the right side. So these weights, it is very important how we choose these weights in order to get first unbiased result. So what does it mean for an estimator to be unbiased? It means that its mathematical expectation is exactly equal to the integral that we are looking for. So there are two very simple conditions that these weights must meet in order to have unbiased estimator, which is something that we want. So the first condition is that all the weights must sum up to 0. To 1. Okay, this is a mistake in my slide. They must sum up to 1. And you can see that everywhere where some of the sampling strategies are 0, the weights also have to be 0. So this doesn't mean that we have a good estimator here. This just means that it will converge to the proper solution if we have weights, if we have such weights. But in order to get these weights, we need to find some special types of weights that actually help us to converge more quickly. Because with this estimator here, we can do much worse than just uniform sampling. And I will show here a special case of this estimator. This is just, we have just two strategies. The strategies in the denominator PF and PG. These are densities that are proportional or at least similar to the functions that we try to integrate F and G. We have this product of two functions. This is something that happens quite a lot throughout the computer graphics. And when we cannot sample from distribution which is proportional to the product of the two functions, we can still have these distributions, and so we can still sample. We can have one strategy that samples one of the functions, and the other strategy can sample the other function, and we can combine them with these weights. So these weights here, they are first. I want you to notice that they sum up to 1, which is one of the important conditions, and this is called the power heuristic. And if you use this power heuristic, the effect of it is that whenever you sample something with two strategies, it weights them in such a way that the better strategy gets higher weight, while if the strategy is not good enough, it will get very low weight. And this is the result from the multiple importance sampling of the problem that we saw a few slides. You can see here there is a lot of noise, and when we combine in this way the two strategies, the BSDF and light strategy, we get this image, which looks obviously much better. And on the right, you can see how the weights weighted the strategies. So the red, let me see, green is for the light strategy, and red is for the BSDF strategy. And this is important. So now I'm going to show you how we apply this multiple importance sampling to our dome light computation. It is very simple. We shoot a ray from the camera. We generate one ray according to the light strategy, which is proportional to the HDR. We shoot one ray which is proportional to the BSDF. The BSDF is this here power function. It is a spherical function in 3D. And then we compute the result of this. We shade this. We trace these directions, and we combine their result using the weights from the multipoint sampling, and we get unbiased estimator, and we get much better convergence. So this is just an example of how we can write our estimator. So the middle row is just the light strategy. The bottom row is the BSDF strategy. We combine them with the two weights, and we get the result. So how do we sample according to environment map? There is one very, very simple way. So I want to outline it because in 2D we are using a little bit different approach than the usual one. So if we have 4 events, 1, 2, 3, and 4, with certain probabilities, these probabilities P1 to P4, they sum up to 1. And we want to have a procedure which samples these 3 events according to their probabilities. So the way this is usually done is to construct the cumulative distribution function, CDF. Here we construct the CDF, and we generate one uniform random variable. This is Xi on the right image. And we have to perform a linear search, or if the table is large, we can perform a binary search in order to find exactly which was the event that we sampled, and this is called the inversion method. So this is the one-dimensional idea which can easily be applied in 2 dimensions, and the way it is usually done for images the way it's done is that we construct marginal distribution for the rows, for instance, choose a row and have these CDF distributions in order to sample a particular pixel. But we decided to use something called sum-area table because sum-area tables were introduced like more than 30 years ago, but they weren't introduced in the context of sampling. They were introduced just basically to compute integrals. But what is a sum-area table? First, each element in the sum-area table is the sum of all the elements that come before this. So the point I want to make here is that the sum-area table is exactly the most natural generalization of the one-dimensional CDF here. And the other thing is that exactly in the same way how we can use this CDF to sample one-dimensional random variable, we can use the sum-area table in order to generate two-dimensional random variables. And so this is a well-known property of the sum-area table. If we take just these 4 elements, we can compute the area of the orange rectangle in this way. So you can just do the math with these areas here. But not only that we can compute the integral of this region, the other thing is that we can very efficiently compute the bounds for binary search in order to sample a pixel from arbitrary region in Okay, what we would like to achieve is we are looking for a data structure which can sample a pixel from the whole image. Now this is easily done. But also we would like to have this structure that also is able to sample from any arbitrary axis-aligned subregion. And this can be achieved with the sum theory table, and it cannot be achieved with the classical approach with the marginal distribution. Okay, so sum theory tables, they have one very big problem, and they are very prone to numerical errors. And I will show some results, and I will show how we fixed this, because we really wanted to use them because of this specific property. But I will tell you some more when I show you the results. Okay. So what is the problem with the classical approach with the dome light? It is very usually the case when the scene is very occluded. Here, this is our scene, but now I have drawn here a simple room, and there is just one window from which light can pass from the environment. And if we use the light strategy, it will direct a lot of rays to the sun, but unfortunately there is a geometry occluding, and so light cannot come from this particular direction. And this thing in practice actually happens quite a lot. And we were looking for a way to solve it. And there are many methods that are based on portals, on artist manual work. Artist place portals on the windows, but we were looking for an automatic solution. So we decided not to. Actually, V-Ray was using portals for many years, but we found that they do not work that well in many cases, and artists do not want to spend time to setting them up. So the other thing, also there are other solutions that use a lot of pre-computation. They use very complex data structures, and usually, for instance, they can help in a situation like this. But if the scene is very unoccluded, like an exterior, they cannot help at all. And they even make the algorithm slower. So again, a lot of artist work is involved. Artists have to decide whether to use one algorithm over another. So we were looking for a solution which first do not require any manual artist work of placing portals, and also that benefit cases like this, very occluded scenes, but if possible, we were looking for a solution that works for the same times, or give at least some benefit in exteriors, but hopefully does not slow them down. So we came to this solution. We decided to tile the environment map into pieces, into equal-sized pieces. We use a very simple spherical grid around the camera. I'll show you in a minute. In this grid around the camera, we store important information, important visibility information that we use after that. We have a learning phase. This was actually very good for V-Ray because we have one prepass that computes some irradiance, that caches some irradiance. This is the so-called light cache, and it traces a lot of paths from the camera, but it is very quick. It usually takes just less than 10 seconds from the whole rendering. But we can use this step, and we can use this step to learn and then to reuse this information. So we reuse these camera paths that are traced in order to find the irradiance cache, the irradiance cache, but also we use this computation to store accumulate some information in the light grid. And then during the rendering phase, we just use the information that was gathered in the light grid in order to do better sampling. So how this is done? This is an environment map. We have this tiling of the environment map. And again, I want to point that we need a data structure that can pick a sample from the whole environment map. And then we need also a structure that can pick a sample just from the tile, and this is important. So this can be implemented in different ways, but we were playing with one of my interns with this Sumteria table data structure. His name is Vasilij Chizov, and he did really great work with this structure, so we decided that we are happy with it, and we decided to use it. Actually, for this particular algorithm, you don't need to be able to sample from arbitrary region, because the regions are fixed. But anyways, the structure works well. So the white grid, as I said, is a spherical grid which is in camera space around the camera, and any point in the scene can be projected to this grid, and each point from the scene belongs to a particular grid cell, like this. And so this light grid basically subdivides the whole space, our whole scene, into regions, into these red regions. And then we have our tiled environment map, the orange arc. I have drawn the tiles. I have put some indices to the tiles. This is T0, T1. These are the tiles. We have the light grid, and I will show now how the learning phase proceeds. Initially, we initialize the whole light grid with zeros. For each grid cell, we have an entry in the light grid for each environment tile. So we start to trace path from the camera. For instance, we can locate immediately. We can project basically the point X and see immediately which is the point, which is the grid cell to which this point belongs, and we can compute the lighting. Now we can see that some rays actually reach tiles, and some other rays, like this, the dashed one, do not reach a tile. So we accumulate this information in the light grid. We write that for this particular cell of the light grid, we have a visible T1 tile, and there are many different ways. We have experimented with different ways in accumulating these tiles. We can, for instance, accumulate transparency. This is one thing. The other thing that we were using was accumulating the maximum tile contribution, and both of them were working almost identically. But we decided to use the maximum tile intensity because it was more robust in some specific cases. Okay, then we continue to accumulate this information in the light grid. For instance, we shoot a GI ray, and this point Y is out of our camera field of view. But no matter, it has a specific grid cell to which it belongs. So we compute the lighting, we accumulate the information, and once the learning phase is done, we just normalize all of the data that we have gathered. We construct these one-dimensional CDFs so that every grid cell can sample can sample only visible tiles. Here with these CDFs, we can, when we are rendering, when we have to do shading point direct like when we have to shade points, when you have to compute direct lighting, no matter if this is a camera array or if this is not a camera array, we can always project the point to the light grid, see for this particular region in the scene which were these tiles that were visible, and then pick these tiles, and with much higher probability we are intersecting the visible tiles. So some implementation details. We implemented this in CPU and GPU, and especially for the GPU part, it was very important for us to use simple grid data structures, especially for the GPU, because a tree traversal introduces a lot of code divergence, and this is reducing the utilization of the SIMD architecture. So we were using these simple grids, simple tiling, simple light grid. Then we measured between 10 and 700% speed up. This was measured for complex production scenes. We were playing with different parameters in order to see which grid, light grid resolution and tiling will work well. So we are using these parameters, which results in only 10 megabytes of additional memory. The learning phase, during the learning phase, we trace 1 million arrays, but these are arrays that we will shoot no matter what algorithm we're using for the dome light, because these rays are computed during irradiance caching. So this usually takes for production scenes less than or around 1% of the total rendering time. So and it is free for us because we are shooting these camera paths. Okay, and also we use these fetch and add instructions in order to avoid synchronization locks during learning. And then we use integer valued SAT. I will show you results. Actually, what we decided to do, we found out that this sum table structure is terribly inaccurate. So when we were using float values, one solution was to use double for this, which meant twice more memory and a lot slower sampling. So what we decided to do, we built this table in double precision, and then we remapped our range in order to use the full 32 bits precision from an unsigned integer, and I'll show some results a little later. So these are results from our algorithm. These are two scenes, living room and office, and I have shown here some small inlets. We have here without our algorithm, and then with our algorithm for the same computing time, and you can see there is observable less noise using our algorithm. And measured times here is when we measure the two solutions, our previous solution and our new solution, for the same noise level, for a comparable noise level. So you can see that we have 6 times faster than before on the GPU, like almost four times faster from the office scene. Then here we were playing with the parameters. This is not. It turned that the algorithm is comparatively stable when we use different resolutions. So it's not so interesting. These are some more results with different HDRs with the living room scenes. Here we have almost everywhere we have like 1.5 to 2 times faster. Here we have almost 4 times faster with our new algorithm. Another thing which is important is to see how this works with exteriors. And you can see the left image. This is both CPU and GPU results. And very important scenario also is when many different points project to the same light grid cell. This is, for instance, the case when we have participating medium, because when we have participating medium, we have to shade on many different locations along the ray, and all of these points along the ray project to the same light grid, but still we have quite impressive speed up. And now I want to show you some results for our Sumteria table sampler. This is a very large HDR image. Actually, I went to our 3D artists and I asked for the biggest HDR images that they have. This is one of the biggest. Also, we were testing with another which was 15,000 pixels wide. And this is also HDR image. So when we were testing our sampler with 32-bit float, it turned that it has observable errors, and you can see that everywhere when the Sumteria table, for instance, reaches a point of high intensity, the accuracy deteriorates after that quite a lot. So this is totally unusable. And our remapping to 32-bit integer gives perfect results. And here you can see 3 different large HDR images sampled with the 2 approaches, with the float and the integer. And you can see that we have 3 to 4 orders of magnitude more accurate solution, more accurate sampling reconstruction with the integer valued SAT. Okay, so this was it. Thank you.